Alright, you guys, today's lesson is about parametric equations. We'll start off with the definition of what that is. So, the graph of the ordered pairs x, y, where x equals f of t and y equals g of t, are functions defined on an interval I of t values is a parametric curve. The equations are parametric equations for the curve. The variable t is a parameter and I is the parameter interval. So that's a lot of definitions right there. But basically, notice that we have variable x, variable y, and now we have a new variable t. And variable t is a parameter. And if you can take a wild guess, t is going to stand for time. So let's practice graphing parametric equations. So the first example, for the given parameter interval, graph the parametric equations. X equals t squared minus 2 and y equals 3 times t. So I made a little chart. On one side I have the parameter interval. In the middle column I have a table, and in the last one I'm going to actually graph it. So the parameter interval is there to tell you when to start and when to stop. And so they can be different. So notice that even though for these next three parameter intervals, they're all different, but we're all going to be using the same x and y. So for the table, you're going to start off, I already have it kind of made here. So it's better to start with t, because t is going to be whatever is provided in the parameter interval. So we're going to start with -3 and go all the way down to +1. I'm going to go in increments of 1. Okay, now to get the x and the y values, you're going to be plugging it into this equation here. So for the x, we're going to plug -3 into t. So that would be -3 in parentheses squared minus 2. -3 squared is 9. 9 minus 2 is 7. So we have 7 here. We can do that again. So that's -2 squared minus 2. -2 squared is +4 minus 2, which is 2. And then you just keep filling in the rest of them by yourself. I already have them figured out, so I'm just going to write them. And then you're going to do the same thing for y. So you're going to plug these t values into that t right there. So we would have 3 times -3, which is -9. 3 times -2, so I'm plugging again this one in here in this t. 3 times -2, which is -6, and then you keep multiplying by +3 all the way down. Now that you have your table, you can go onto your graph. Obviously we only have an x and y direction here, so we're only going to be plugging in these points. So we're going to start with 7, -9. 2 and -6, -1 and -3, -2 and 0, and -1 and 3. And then you're just going to connect it as best as you can. Mine is hideous, but it's okay. And you're not going to put arrows on this because the parameter interval is very specific that it stops at -3 and +1, so you're not going to want to put arrows. You're going to leave them as close points. Okay, now let's try different parameter intervals. So we're going to be using the same formulas but different numbers in the parameter interval. So now instead of starting at -3, we're going to start at -2, and we're going to go all the way to +3. And then again, we're going to be plugging in to here again. So this t value in there. So -2 squared minus 2, which again, that's 4 minus 2, which is +2. The same thing for -1 in there. That's -1 squared minus 2, which is 1 minus 2, which is -1. And you would just keep repeating that process for all of the numbers in the parameter interval. And then the same thing for y, so you're going to be multiplying it by 3, by positive 3. And then you're going to plot, again, only the x and the y values, which are the x and the y axis. So we'll start with 2 and negative 6, negative 1, negative 3, negative 2 and 0, negative 1, positive 3, 2 and 6, and 7, 9. Okay, so you can see that these two are similar. They both have this like parabola shape, but just one starts earlier, one starts later, and one ends and starts whatever. You know what I'm saying? So yeah, they're similar right here, but let's do another one so you can see. So again, do your table, put in your 3 variables. The parameter interval tells us to start from negative 3 and go all the way down to positive 3. And I'm going to go by increments of 1 again. We are still using the same formula. So t squared minus 2. So down here, my first t is negative 3. So we'll start negative 3 squared minus 2, which is 9 minus 2, which is 7. And then you keep doing that for all of the other numbers. And then the same thing for the y, we're multiplying by 3. And then you plot the x and the y coordinates. 7, negative 9, 2, negative 6, negative 1, negative 3, negative 2, 0, negative 1, positive 3, 2 and 6, and 7 and 9. So this one a little bit is basically combining these two. So you see how this one stopped right here. This one started late but went further. And this one is kind of piecing everything together as one full parabola. So that's the first example. Let's try another one. Now we're going to have different equations. So the parametric equation, x equals 3 minus t squared, y equals 2 times t. And now we have 2 different parameter intervals, one from negative 2 to 4, one from negative 3 to 3. I'm going to make my table for both. And we will start putting that parameter interval into the t column, again going by increments of 1. And then so we'll plug in to 3 minus t squared. So 3 minus negative 2 squared. This negative 2 is coming from here. So that's 3 minus 4, which is negative 1. This negative 1 will go here. So 3 minus negative 1 squared. 3 minus 1 equals 2. And then you just keep going in that fashion. And then for the y's, now we're multiplying by 2. So whatever these numbers are, just multiply them by 2. Okay, and just like last time, you're only going to graph the x and the y coordinates into here. So we have negative 1, negative 4, positive 2, negative 2. 3 and 0, 2, 2, negative 1 and 4, negative 6 and 6. Negative 13 is kind of off the charts, but I'll put it somewhere in this blank space. So pretend that's 13 over there. And so connect the points until you see a little parabola shape kind of cut off. So let's repeat the process with the second parameter interval, which is negative 3 to 3. So again, you're plugging them into 3 minus t squared, and 2t. So 3 minus negative 3 squared, this negative 3 right here for this t value. 3 minus 9, which is negative 6. And then just keep filling them in. And then for the y, again, multiply it by 2. Or multiplying the t values by 2. That wasn't very specific. Okay, now that we have those x and y coordinates, we're going to plot them on the graph. So negative 6, negative 6, negative 1 and negative 4, 2, negative 2, 3 and 0, 2 and 2, negative 1 and 4, and negative 6, positive 6. Okay, so you can see how they're similar, just one extends further this way and the other one extends further down. Again, don't use arrows because they are not going to infinity. They have a set start and stop value. You can also graph these in the calculator. I'm going to provide the calculator steps here for you. Just randomly over here somewhere, I guess. I'll put them down here. Okay, so the calculator steps on the end spires. So the first thing you're going to do is open up a graph, and then it's similar to when you were graphing polar graphs. You're going to go to graph entry, which is, I believe, number 3. When you're there, you're going to select the word parametric, which I believe is above polar. And then you're going to get a screen, and then you're going to plug in the x and the y. And they're always different, and they will provide that for you in the question. And then you're also going to plug in the parameter interval, which they will also give you in the question. Okay, so plug in the parameter interval. And then you can trace as needed depending on the problem. They might ask you to try to find something on the graph. Okay, so I'll show you how to do that. So you're going to start by pressing menu, then add a new graph. You're going to put graph entry and then press 4 for parametric. You see you get an x and a y. And now let's put in the formula for example 2, which is 3 minus 2 squared, and 2t. The first parameter interval was negative 2 to positive 4. Ignore that again, press enter. And then so you'll see it looks like the one we had in our notes. You press tab. Just change the parameter interval to negative 3 and positive 3. Again, matching the one that you have in your notes. If you press menu trace, again, it looks different on here, but if you press trace and then graph trace, you'll see the x and the y coordinates as well as the t, the time. So the values here should match up with the ones you have in your table. So the very first entry we have on that table is for when t is negative 3, and we do have negative 6, negative 6. If you go up and keep tracing negative 2, that was our next entry, which was negative 1, negative 4, so that matches up correctly. So you can use this to trace the graph. Then you should be able to just type a number. So let's say negative 1, and notice that this like little box comes up. Whatever number you type is going to correspond to the t variable. So notice that right now we're at negative 3. When I press enter on this negative 1, it's going to automatically take me to negative 1. I could put any number. Let's say I put 0.5. 5, 6, 7, or something like that. And so the time changes and you get the exact coordinate points X and Y when the time is this decimal. And so that could be helpful for when you have word problems when they are trying to have you analyze the graph or something. In conjunction with parametric equations, we also have projectile motion. All of these come straight from your formula chart. So we have the horizontal distance, vertical position, vertical free fall motion, and then gravity. The horizontal and vertical, they kind of start out the same, except one is cosine and one is sine, but then the vertical one has some extra stuff to it. So x equals t times v sub 0 cosine theta. So we can write down our variables off to the side. So the first variable I see is t. So t is going to be time, like I told you earlier. The next one, v sub 0, that's going to be your initial velocity, or your initial speed. That can be used interchangeably. So I'm going to just put that in parentheses. Okay. So we have t, we have v sub 0. Cosine is just a trig function, but theta is still going to be your angle measurement. Okay, so for the vertical position, we still have t and v and theta, which we have already labeled. The next thing we see is g. G is gravity. Okay, then we got t again, and then the next thing we have is h sub 0, which is going to be your initial height. So anytime you have a subscript of 0, it's usually the initial of something, the starting point. So that's the vertical and horizontal distance. Now, gravity can be either 32 or 9.8, depending on whether the question is given in feet or in meters. So if they give you this one versus that one, then you use 32 versus 9.8. So it just depends. So let's try a question. So Kirby hits a ball when it is 4 feet above the ground with an initial velocity of 120 feet per second. The ball leaves the bat at a 30-degree angle with the horizontal and heads towards a 30-foot fence 350 feet from home plate. Does the ball clear the fence? If so, by how much did it clear the fence? If not, could the ball be caught? All right, so there's a lot going on, so I'm going to start color coding some stuff. So we know that the ball is 4 feet above the ground. We know that there is an initial velocity of 120 feet per second. I see that we have some kind of 30-degree angle. Notice also that the units are feet per second, meaning that we're going to be using this gravity of 32 instead of 9.8 because they use feet per second. So let's write down x and y because we're going to need to have x and y for when we go and plug it into the calculator. So x equals, and we're going to be using that horizontal distance equation. So x equals, so t, we don't know time, so I'll leave it as t. But the initial velocity they did tell us was 120. And then we have cosine, and the angle they said was 30 degrees. Now we'll do y. So again, we don't know time. Initial velocity is 120. Now we're doing sine. The angle is still 30 minus 1/2. As discussed, we're going to use the gravity that's feet per second, which is 32. We don't know t. And then the initial height, it said that he hits the ball when it's 4 feet above the ground. So that's going to be the initial height. Okay, so now from here, you can go ahead and put it in the calculator. Also, make note that time cannot be negative. These are real world problems. We don't go backwards in time. We don't go, back into the past. So time cannot be negative. So make sure that you're starting at 0 instead of any negative numbers. So after you graph this in the calculator, you should get something that kind of looks like this. I'm going to kind of try to sketch it as best as I can. So they tell us that there's some kind of home plate. So pretend that's my home plate, and it's getting thrown from 4 feet above the ground. So if the starting point is the origin and it's 4 feet above the ground, then I know that this point has to be 0, 4. Then they said that there's some kind of 30-foot fence. So I can kind of draw that over there. So I'll label it so you know what this red line is. This is the fence, and the fence is 30 feet high. And then we're basically going to graph it to see what the trajectory is after Kirby hits the ball. Alright guys, when you guys are typing this, you're going to want to make sure you have the times symbol in between all of the numbers, because it may or may not work if you just type it next to each other. So just be very purposeful to put the times in between anything that is being multiplied. And again, for the parameter interval, we don't know how long it's going to take for that ball to hit the ground. So I'm just putting a random number, and then we can see if it works or not. So I am too zoomed in, so I'm going to zoom out a little bit. Oh, okay, perfect. So you should get a parabola kind of line that looks, something maybe like this. And so they said the home plate from the fence was 350 feet away. So in the calculator, you're going to want to figure out after you have gone 350 feet away, what is the height right there. So we're looking for the point that's 350, and we're trying to figure out why to see if the ball cleared the fence. So did it go over the fence, or was it low enough to where the ball can be caught by a player? Or was it too high up? It didn't clear the fence, but no one can catch it. So we got to figure out what scenario is happening here. So you're going to trace the graph. So notice that we start here. The home plate is 4 feet above the ground. So this is 4. And we want to figure out the height of the ball after it has gone 350 feet away from home base, because that's where the fence is. So we're going to trace it, and then we're just going to watch out for the x coordinate until it hits 350, because that's how far away. So remember, there's like some kind of imaginary fence somewhere around here at the 350 feet mark. And so we want to know the y coordinate when x is 350. So I'm going to kind of trace this until I get there. Okay, so we go from, okay, so there's 350. And so the y coordinate, the height is 24.6. So it took about 3.37 seconds for the ball to go that high. So essentially, it did not clear the fence. Remember the fence, let's say the fence is somewhere up here, because it's a 30-foot fence. So the ball only went about 25. So it didn't go over the fence. And no one can jump 25 feet high into the air. So the final answer would therefore be that no one can jump that high. So the ball cannot be caught, and it did not clear the fence either. It kind of just hit the fence and just fell. Okay, so now we answer the questions. So part A, it does not clear the fence. Because the height is less than 30. So when you traced the graph and you went 350 feet along the x-axis, you will see that the y coordinate, so this point right here, is 300 350 and 24.7. So the ball missed it. It missed clearing the fence by about 6 feet. So it did touch the fence. It didn't go over. Now, the second question is, can it be caught? Unless someone can jump almost 25 feet in the air, no, the ball cannot be caught. So it cannot be caught because no one can jump 24.7 feet high. That's pretty high up. So there is one example of projectile motion. Let's try another one. Nancy hits golf balls off the practice tee with an initial velocity of 180 feet per second with 4 different clubs. How far down the fairway does the ball hit the ground if it comes off the club, making a 15-degree angle with the horizontal? Okay, so we can label some things here. So we have an initial velocity of 180 feet per second. I also see the units for feet per second. So again, I'm going to be using the gravity, which is 32, because of this feet per second that they match up. We know that the angle is 15 degrees. So let's plug everything in that we know into the formulas. So x equals... So t, we don't know t. The initial velocity is 180. And then cosine of 15. Now for y, the same thing, but we're going to have sine. And then we're also going to have minus 1/2. The gravity, feet per second gravity, which is 32. And then t squared plus the initial height. Now, for those of you guys that don't know anything about golf, so if I draw what the graph would probably look like, it says that it's getting thrown off of a practice tee. And a practice tee is basically like a little thing that goes into the soil where the little ball is gonna be at. That's the golf ball. So if you think about it, if the tee is going into the ground and the ball is right on top of it, the initial height is going to be 0. Because it's on the floor. You're throwing it, from the practice tee. So how far down the fairway does the ball go after it gets thrown 15 degrees? So we're going to graph this, and then we're going to trace it to see, how far it goes. So x equals t times 180 times cosine of 15. For y, we have t times 180 times sine of 15 times, minus 1/2 times 32 times t squared plus 0. And for the parameter interval, I guess we can keep it at 30. Whenever you're doing this on your own, you can just mess with the parameter interval until you figure out whatever you need to find. So if you need to figure out when the ball hits the ground, if you need to figure out how far it went at a certain time, and you want to see the whole projectile motion, then just make this kind of big enough where you can see the full picture, and then press enter. So this one, for the second example that we did, notice that it's a little bit lower. This one starts at 0 because remember the tee, the practice tee is on the floor, so the golf ball is also on the floor. And so you can see that we want to figure out when the ball hits the ground. So we're going to trace this. and we want to figure out when the height is 0, right? When the ball hits the floor, the height is 0, and the height is y. So we're going to be looking at this second number until it hits 0. Okay, so notice that we jumped from 2 to -2. So we're going to have to maybe plug in some t values to figure out when we're at 0, because it goes from 2.87 to 2.97. So that's just about 10 decimal places that we can put in. So it's not going to be 2.87. Let's see if it's 2.88. So remember, you can just type a number in and it'll adjust it for t and then give you the x and y coordinates. So that's 2.88. We're still not at 0. Let's try 2.89. We're at 1, so we're getting closer. Let's try 2.90. Okay, we're 0.5, so we're almost at the ground. Let's try 2.91. Okay, we're at 0.08. Let's try 2.92. Okay, now we went down to into the negative numbers. So we don't want to be in the negatives. So let's go back up to 2.91. Right now we're at 508. 2.91. We're at about 506. What if I do 2.915 maybe? Okay, we can't do that. Let's see, 2.9. It's kind of just, you just put in random numbers until you get it. Okay. Well, 2.914. Okay, 2.91. Okay, well, let's just go with this because this is pretty close. So it's pretty close to 0. It's close enough. So we'll just say it went 506 feet away. So specifically, if I could get to 0, let's see. I could trace. So you can do traced step. So notice that here when we were tracing, and I just graph traced, we're going by random numbers of t. So we start at 0, we go up to 0.11, 0.20, 0.30, 0.40. So we're going up 0.10 every time. So let's see if I can, if you go to trace and then trace step, instead of having it be automatic, let's enter a value. So instead of 0.10, so right now we're at 0.10. I want it to be smaller, so maybe like 0.01, and that way we can get a more exact measurement. So now when we trace it, and we already knew we were somewhere around 2.91, we just have to get closer. So notice that I'm moving it, and we're going 0.66, 57. Okay, regardless of how close we get to 0, notice that it's just staying around 506. So for all these really close values of 0, it's just about 506. So we can just estimate about 506 would be the height of, not the height, the distance the ball traveled. And so yeah, so you just have to use this depending on what the problem is and what they're asking you for. So whenever the ball touches the floor, that's how you're gonna figure out. So when it touches, is obviously we're gonna figure out how long did the ball travel. So you're gonna want to figure out when y is 0, and then you want the x coordinate when y is 0. And after you trace it, you'll see that it's about 0.25. So, final answer, the ball travels 506.25 feet. And it takes, so after you keep, when you're tracing it, you can figure out how long it takes. So the ball travels 526.25 feet in 2.91 seconds. Okay. And so that's all I have for today. I hope you learned something, and I'll see you guys next time. Bye.